Welcome to the presentation on analog to digital converters, or ADCs. Here we show a digital ramp ADC, which are many types of ADCs that will be used using this similar type of architecture here. And this is very similar to what we're going to build and troubleshoot when we do our final. What we have here is basically a counter. And this counter is going to count from 0 to 256. And then we go into a DAC, a digital analog converter. So this guy's producing a digital pattern, 0 to 255, and is fed into the DAC, which is producing an analog voltage in a stair step. Okay, so what we have is this analog voltage clicking up, and we put in an analog input. When these two exceed one another or cross, we enable this gate and it locks this in, which goes out to a latch. So when these two cross, whatever count it's on, and the voltage is matched between the analog and our unknown, it latches it into a data latch where we could display it. And this is the typical type of DAC that we'll be using. Here's an 8-bit tracking ADC, basically very similar to the last one. The downside of these is that we may have to count all the way up to 255 in order to find the unknown voltage. So this could be kind of slow, but basically it's just a little bit different variation of the last one. Here's a different configuration called a single slope ADC. Basically the same thing. They're just trying to get faster, better, and a little more accurate output. Here's a dual slope ADC. Basically it's similar. We're just using an integrator and some other things here in order to do it faster, better, more accurate. Here's a different type of flash. This is only 3-bit. We have separate comparators. And we have a voltage divider, and when we put in this analog input, our unknown voltage, it quickly goes through and selects one of these, and then gets trapped in our priority encoder. So this is the fastest. This is a one-step deal. Very quick. We need a lot of complicated circuitry in order to pull this off, but it's very quick. This is a successive approximation ADC, where our slope ones are going to take up to 256 steps. Our flash is 1 step. This one is going to be 8 steps. So this 8-bit successive approximation, it's 8 steps. So the first thing it does is it compares it in binary. First thing we do is we look at our unknown voltage, and we compare it to 5 volts. If it's greater than 5 volts, we're going to set it as a 1. If it's less, it's going to be a 0. Then we're going to take a look at the remainder, and we're going to look at it 2.5. Is it greater or less? Then we're going to take what's left, and we're going to see if it's greater than 1.25 or less. If it's less, it's 0. And we continuously do this with smaller and smaller variables, and then we're going to set a binary 8-bit pattern, and it's going to represent the output. And this one's 8 bits, fairly quick, fairly accurate. Here's our schematic of our ARC 1-digit voltmeter, which we'll be using for our lab final. And let me go through this, and we'll go into greater detail when we start troubleshooting it. Basically what we have here is a clock. We're using a 555 timer as a clock. We're utilizing a inverter, a Schmidt trigger inverter, so we could square up and make a better signal coming out of our clock. We're going to feed a 7490, and we're going to have it set up in the BCD mode. And we have our binary weighted resistors fed into an op-amp. So this is our binary weighted summing amp. Here we have an adjustment so we could zero the output. Here we're going to have a negative going stair step. We're going to go through a unity gain based on the same size resistor, so we're going to make a positive going stair step. So our first test point is going to be a positive going stair step 0 to 9. We're feeding that into a LM339 comparator. Here's our unknown voltage, which will be set. We're going to compare these two, and when they compare, we're going to send a pulse. It's a differentiated pulse because this is an RC circuit, and we will have a pulse, and then we're going to run it through another pair of inverters. So we're going to square it up. So this is positive, this is going to make it negative, and this is going to convert it to a positive pulse. We're going to send those positive pulses into our data latch. So we're going to lock in that number in digital and binary, and we're going to convert that binary number to a 7-segment display based on the 7447. All these components we've used already, and we will get a chance to look at them in closer. Here's a little block diagram of what we're looking at here. So we have our binary generator 7490 and our binary weighted, and this is our deck. All right, so we're going to make a negative going stair step, which eventually we're going to convert to a positive going stair step. So this is our digital analog converter. So we put in a digital number, and we got an analog output, and it's going to be a stair step. We're going to put it into our comparator. We're going to put our voltage reference, which is our unknown voltage. And when these two cross, our voltage reference and our voltage ramp, we are going to trap that. So here we're showing our second part of our comparator trigger circuit here. We have our 339 comparator. The output of these, when they cross, we're going to get a square pulse. That pulse of a DC pulse is going to be converted to a differentiated signal. So it's going to be a positive going spike. That spike, that differentiated spike, is going to be converted to a nice pulse by going through our Schmidt trigger of our inverter. So it's going to be a negative going pulse, then converted to a positive going pulse, and these signals are going to be set into our data latch, which is going to latch the output. So what we have, if we look at the scope here, we have a positive going analog voltage. Once they cross, then we're going to switch our comparator and then create a spike, a differentiated signal.